Uh, well, hello everybody. Welcome to August's OARC talk. My name is Mark 2M0IIG, and I keep forgetting to introduce myself, so I'm glad I remember this time. We have a very interesting talk, which I'm looking forward to this evening from Simon, EI3JDB. Get onto that in a second. Just to give you an idea of what's coming ahead in the next few months, I do have a September and an October talk booked. We have satellite operation for beginners, how you can get into working satellites. That's from John, J5 JFS. And then in October, we have Linux in Ham Radio by Hibby, who a lot of you will know from OARC, and who has created the Hibbian amateur radio distribution full of all sorts of wonderful tools and whatnot. I don't have a November talk as yet, but stay tuned. Hopefully, I'll have news soon. I've got a couple of irons in some fires, and then rounding out the year in December, as we begun in January, I'll have Jonathan Naylor, G4KLX, who will be talking to us about the history of packet radio in the UK. If you want to do a talk, you want to come and entertain us all for 45 minutes or so, do send me a DM and let me know. I am booking talks for 2027 now and doing the plans. So, without further ado, as I said, tonight's talk will introduce Simon, EI3JDB, and the title of his talk is Long Wave Listener, and he'll be telling us tonight all about the world below 3 megahertz, MF and below, and how you can get into listening to that and do that on your own. So I will hand over to Simon now. Thank you, Simon.
Thanks. Okay. First of all, let me see if I'm sharing. Am I sharing my screen? Can you all see my screen? You can't, can you?
It just stopped sharing, Simon. It was, and then it stopped.
Okay. So there we go. As I was just saying, I'm quite happy to take questions, or if anything's not clear, do please shout out or ping something in the chat, and I'll slow down or take the pace that people understand. So what I'm going to talk about is about what's going on below 3 megahertz, and actually what's going on way below 3 megahertz, because it's not just top band. There's lots and lots of things way down in the really low frequencies. So let me just give me a second. My screen has frozen. There we go. So it's all very laggy. Here we go. So my name's Simon, EA3JDB. I first started experimenting with VLF about 50 years ago, nearly 50 years ago, as a teenager, with the help of Ron G8MEI. I was living in Cambridge at the time. He's unfortunately now silent key. I only really started amateur radio a couple of years ago. I wanted to start as a teenager, but I never got a chance to get Morse sorted out, so I went into professional radio instead. My day job is kind of around 3.5 to 4 gigahertz. So this is kind of the opposite end of the spectrum for me. But I think what's going on in HF, MF and lower is much more interesting. And I also think it's much more accessible. I got started by building things like crystal sets, as some of the older people here will have done. You can't build crystal sets these days. Well, you can, but there's nothing to receive. But I think these frequencies, you can still build circuits very easily with very cheap components without worrying too much about layout or complexities of design. So I think this area is actually a really good area to start getting involved in radio and to get an introduction to radio. So that's what I'm going to talk about. Please wait while my computer catches up. So, first of all, how to listen. As I said, you're all amateurs, or most of you are amateurs. You probably got a lot of these things in your shack already. The sorts of things you're looking at for the antennas, I've said long wires and loops and coils. I think a ferrite rod antenna is one of the best things if you're limited in space for this. Later on, I'll be showing a 60 kilohertz ferrite antenna, and it's very effective. Loop on ground is another possibility. The signal received by loop on ground is attenuated, but these frequencies actually pass into the ground quite easily, where a lot of the higher frequencies don't. So loop on ground can actually work quite well. If you want to receive these signals, I have an old Kenwood TS570 that goes down to 30 kilohertz. A lot of the older radios do go down. If you're trying to receive the amateur bands, you probably need a preamp because the amateur bands really don't have very much power in them at all. I think more modern radios don't always go down quite as low as the older ones do. But if you want to make your own, again, as I was saying, construction of these frequencies is really a lot simpler than any other RF construction. You don't really have to worry too much about layouts. The components are cheap. And as I'll be showing you in a little while, the equipment you need to kind of test and debug it is very, very cheap now. And again, you probably got it in your shack. The other way you can receive is with a sound card. Any sound card you've got will allow you to receive the bottom 20 kilohertz. A lot of sound cards nowadays will sample up to 192 kilohertz. So those will go up to 96 kilohertz receiving. And you more or less just plug your antenna into the microphone input of your sound card, and it just works. And a very useful cross-check I've found, the University of Twente Web SDR in Holland goes down to DC. So you can think, I wonder if this signal the one that I'm supposed to be receiving, or is it some local noise? You can look at their web SDR and you can see the signal, and you can compare on your waterfall to their waterfall and get a clear picture of how it's doing. Propagation at these frequencies tends to be quite long because the waves are so long. So chances are most signals you're going to be receiving on these islands, you're also going to be able to receive in Holland. Just be patient with my computer. So just quickly, what I have in my shack is I have a top band Skyloop, which is something I'm very fortunate to have. There are advantages to living in rural Ireland, and that works very well almost down to DC. So that's kind of my reference antenna. But as I said, I've constructed other antennas which are a lot more suitable for people who don't live in a field. I use a Kenwood, which gets me down to 30 kilohertz. I use simple phantom power preamps, and I will show you the circuit for one of those. My sound card is a thing called a Scarlett Solo 3, which is a semi-professional sound card and has fantastic low noise. It's certainly overkill for this sort of thing, but it's a great piece of kit. They're not that expensive on Amazon. I'd certainly, if you want one of those, you'll certainly get good results. So again, please be patient with my computer. So just talking about construction, as I said, the components here are cheap. You're within an order of magnitude of audio frequencies. So very often any transistors and any other components you're buying will really not be very expensive at all. You can use op amps quite often, just simple audio op amps. Layout is not critical because the wavelengths are so long that everything's tiny. And the test gear is cheap. as I was saying, you can have your sound card can generate signals for you. Your sound card can act as an oscilloscope. Your sound card can even act as a spectrum analyzer. Now, in radio, we use spectrum analyzers. For a lot of spectrum analyzers, the frequencies that we're interested in, you could buy a car. In the frequencies I use at work, you could buy quite a nice car for the price of a spectrum analyzer. But at these frequencies, your sound card will do. So that makes this really accessible compared to a lot of other frequency work. So components are cheap. This is a circuit for a 60 kilohertz receiver I have screwed to the end of the house. This is a ferrite rod antenna that I bought off Amazon for a couple of quid. Capacitors to tune that to 60 kilohertz. J309 is a pretty well-known JFET. Again, they're cheap. There's lots of them around. An ordinary resistor, I've used through wire in this case, which you wouldn't normally use for RF because they're spiral wound, so they have a lot of inductance. But at these frequencies, it doesn't matter. So it's what, 5 components on a piece of strip board. So something like this. Again, you can see layout is really not critical. I've just put them into a weatherproof box, screwed a BNC on the bottom, and you can see the wires are just hanging off the strip board, and the strip board's just connected to the ferrite rod. Really very, very simple. And there's just a little cluster of 3 capacitors here to do the tuning. So just fiddle with these and select on test until we get good resonance at 60 kilohertz. And I just skipped over 2. So here is my picture of what my what the low frequencies look like on my top band Skyloop. So you can probably see this goes up to 96 kilohertz, and it's basically just a waterfall. The frequency I'm interested in, 60 kilohertz here, you can see this kind of dots and dashes thing going on here. That is the time signal, the MSF time signal being transmitted from Anthorn in Cumbria. And that was the signal I was trying to capture. So this has all just been picked up by plugging my Skyloop into a sound card, a little bit of GNU radio companion to just feed the output into a visualizer that shows the waterfall, and that shows me what I can receive. And then for comparison, this is what it looks like when it's been received by that circuit I've got constructed up there. You can see that the noise has been amplified and lifted in this little area here, which is the tuned circuit. You can also see this very strong line here with a harmonic here and another harmonic here and another harmonic here, which is quite close to my signal. This is around 16 kilohertz and is being generated by my computer monitor. So in spite of the fact that this is plugged into, this is screwed to the outside of the house, it's still got a very strong signal from the computer monitor in the house. And this is one of the downsides of these frequencies. As with HF, there's a lot of interference from other components around, electronics that aren't really designed as well as they should be. And this is the reason why I put this thing outside in the first place. But you can see, because you can visualize how the signal is at every step during your circuit, it's surprisingly easy to design circuits to receive and even to transmit these frequencies. Okay.
Simon, may I ask a question?
Yeah, go ahead.
Hi, this is Michele, Mike. What is connected to the BNC of the radio? So do you connect the sound card that acts as a digitizer or what?
Yes.
Sorry if it's a stupid question.
No, there's no stupid questions. What I've done, I've just taken the antenna output and fed straight into the sound card itself. So just into the microphone input of the sound card. In the case of this circuit, there's a phantom power circuit required for it. So there's just a current source and a capacitor and inductor outside. But for most of these receptions, even a passive antenna, you just plug straight into the microphone input of your sound card, and then GNU Radio Companion will find the sound card input, and you can do signal processing to end up with a display like this. Does that answer your question?
Thank you. So the circuit is an amplifier and a filter.
So yeah, this circuit here is a tuned circuit. So this piece here is your normal sort of tank circuit that you'd have around a ferrite rod, and then there's an amplifier here. The input of this JFET produces varying currents through here, and the varying currents are picked off by the phantom power.
Is that all good, Mike? Can we move on? I think we can. I think he muted.
Thank you. Yes, absolutely. Yep. Sorry.
No problem. So just let my slides catch up. So this is the thing about noise. You've probably seen this graph. We in HF normally work in this kind of region, and we know what it's like when the sun has a difficult day. Nobody's doing anything because we have enormous amounts of noise. So basically, these lines here are showing how much noise you get at the different bands as the sun ranges from being quiet to being very bad-tempered. So this is the amount of natural noise you get at the different frequencies when solar conditions vary. And the amount of variation we get here is more significant as you go to lower frequencies. I'm hoping you can see the frequency scale down here. So firstly, yes, we've got more noise, but you can also see it's more sensitive to solar activity. So in this case, we were at 60 kilohertz, which is up here. Even on a quiet day, the signals we're getting here, that's about 90 dB, is 50 dB, so 100,000 times greater than the signal level we'd receive on the noisiest days when the sun is stopping us playing radio in the HF bands. So the amount of signal that you're receiving and the level of noise that you're getting from solar sources and from other natural sources means you don't need these receivers to be particularly sensitive, because you could have a receiver that was sensitive down here for HF work, but you can see it would have so much headroom that you don't need those levels of sensitivity. And a circuit that's sensitive to tens of millivolts will certainly be adequate for these kinds of frequencies. And that in turn is why the old crystal sets used to work, because you didn't have very much, you had no amplification. It's just a tuned circuit and a rectifier. But even then, with a sensitive earpiece, you could still listen to broadcast transmissions. And there's no way you'd be able to do that in HF, because the receivers are all more sensitive and the transmitters are all much lower power relative to the receivers. And the same thing applies for man-made noise. In this graph, there's more or less a line drawn showing that the man-made noise rises as you go further down the frequencies. And you could see that in the previous picture. There's a lot more noise in the left-hand part of the picture here. And some of that's natural noise, some of it's man-made noise. These kind of red bars here are 50 hertz mains hum. So as you go further up, it gets quieter. but even up here in the kind of 80, 90 kilohertz region, it's still much more noisy than any level we'd receive in an HF equipment. So, and also you don't have to have a very sensitive receiver. But the other thing I'll say is that below 10 kilohertz or so, noise is actually the most interesting thing you'll hear, because we are not just hearing the sun, we're hearing effects of lightning and other things that are actually quite audible, and you can hear these things around the world. So let's get on to that. You're all familiar with these kinds of pictures for HF propagation. The idea that you transmit a signal from your transmitter, it bounces off the ionosphere and comes back down again. And this is a very simplified picture. Obviously, there's multiple layers in the ionosphere, and it changes from day to night. But at night, also, the higher MF frequencies are doing the same thing. They're bouncing off the ionosphere, they'll then bounce off the ground, and that way they'll propagate around the world. But this distance here is a few hundred kilometers or even less at night. So it's not actually very far compared to the wavelengths. And when we're looking at MF signals and lower, certainly when you're down into the kilohertz region, the wavelength is as long as this gap here. So this picture isn't accurate anymore. And instead, oh, that's the wrong way. You would have something that is more like a waveguide. We use waveguides in gigahertz transmissions, and they're normally small pieces of pipe or small pieces of duct on the circuit or in the enclosure. But at these frequencies, because the wavelengths are so long, the Earth and the ionosphere form a waveguide that carries the signal like a transmission line. And like a transmission line, that means the frequency varies. You're all familiar with the idea that the speed that your signal travels down a transmission line is a fraction of the speed of light, and sometimes quite a small fraction of the speed of light, maybe a half or is even less. And we get this same effect here with the ground and ionosphere. So these signals don't travel around the world at the speed of light. They travel slower than the speed of light. And how fast they travel depends on their frequency. So at slower frequencies, they travel more slowly. It also depends on the layers here and on what the sun's doing. But it can have a peculiar effect where a signal is generated, and if it's a broadband signal, particularly if it's a lightning signal or something like that, you can get a lightning strike over here, and the high frequencies of it travel quickly, and the low frequencies travel more slowly. So close by, you'll hear a click. Further away, you'll hear the high part of the click, then less and less and less frequency, and you'll hear a whistling note that that descends in frequency as the different parts come in. And so listening to lightning close by, you'll hear clicks. Listening to lightning further away, maybe in other parts of the world, you'll hear other sounds. Obviously, this doesn't work very well during the daytime, because one of the things I haven't shown here, there's a D layer here, which absorbs everything below maybe 10 megahertz or so, and that is quite happy to absorb these signals. So they don't travel very far during the day, but at night you get to hear lightning that may be halfway around the world, and this is where you get to hear the peculiar sounds. So what I will do, I'll just take you through what spectrum there is, and I'll talk a little bit more about those natural sounds when I've just described the spectrum. So here's a kind of summary of what the spectrum has. Down here at the bottom, 1 to 10 kilohertz is those funny noises we were talking about. tweaks have a slight delay for the lower frequencies. Whistlers really do. They sound like a slide whistle. And the dawn chorus, when you're in the grey line, you get all sorts of grey line effects that mean you can end up with some really strange sounds that sound like maybe birds or frogs twittering away. And I'll play some of those for you in a moment. Coming up, the SAQ transmissions, I've wibbled about those on OARC several times. They have a transmitter that transmits twice a year, and I'll talk about that in a bit. In this band from about 18 up to about 145, because these signals transmit around the world, but also penetrate into the ground or into water, they're frequencies that can be used to transmit to submarines. They only transmit in one direction, but the frequencies are used, and there are various submarine transmission signals come from around the world. The MSF time signal I was just talking about, and there's an equivalent German time signal, and there are others. We have an amateur band in 200 meters, which is 135, 137 kilohertz kind of region. So what we would have called long wave back in the day. And that you can transmit on that. And if you can construct a transmitter, you can transmit around, certainly around the nighttime side of the planet. Again, construction here is surprisingly easy, because although you need quite a lot of power, a lot of audio transistors will work well at these frequencies. So designs that can be used for powerful audio transmitters will certainly work on these frequencies. There's an FSK up here. The long wave broadcast band is now empty, certainly here in Europe. Some of you will have heard Radio 4 switch off a couple of weeks ago. So there's this huge chunk of bandwidth just with nobody in it. There's a whole selection of these things called NDBs, which are navigation beacons used by ships and aircraft. There's another amateur band here. The medium wave broadcast band is now empty as well. And up here, we have top band, which is probably where most of your normal kind of radio amateur activities start, from top band and upwards. So that's a kind of quick look at it, and we'll just go through those parts of the spectrum and what you can expect to hear on them and how they work. So natural signals, you'll get the normal spherics we'll hear during the day would be clicks you'll hear of nearby lightning. You don't hear the lightning propagating through the Earth ionosphere waveguide, because the D layer stops that happening. But let me just try and play some of these, and hopefully they won't be destroyed by Zoom's noise cancellation. So these are tweaks. And you can hear that the frequency just kind of drops a little bit. There's a kind of slight dropping note in them. And some people think these sound like bird song. And this is, you'll hear a lot of these in the kind of grey line time, the dawn chorus. So whistlers are the same, but much more drawn out because they've traveled a lot further. So the frequency difference is quite a lot different.
They're like fireworks with explosions, Simon. That's cool.
Yes, the crackling is the fireworks, but the whistling is lightning from a long way away, coming halfway around the planet. And you should, if you can get to a fairly low noise place, be able to hear these just with a sound card and some kind of antenna, because these are actually audio frequency. This is not demodulated. This is literally recorded from audio frequency. Right. So you can receive these, as I said, with a sound card. Filters against mains hum is probably all you'll require. Alternatively, people take battery equipment off when they're in away from electrical equipment, and then they can receive these. There's various circuits online for making dedicated receivers. Again, these are all audio frequencies, so there's no RF layout concerns. There's no expensive components in this. It's literally just op amps kinds of things. And because you're although you'll get the crackles, the spherics during the day, you'll get the interesting things you'll hear at night, kind of midnight, and then on into the grey line conditions on times when there's lightning, which there normally is somewhere in the world. So this is a circuit I put together in GNU Radio Companion to do this. Again, you see this audio source is just taking straight from a sound card, just microphone input. This part in the middle here is a comb filter. So 48K, a delay of 960 is equivalent to 50 hertz. So you're taking a 50 hertz signal, you're delaying it by one cycle, and then subtracting it from the input. So if you've got a 50 hertz mains hum, you would be subtracting the mains hum's last cycle from the current cycle, and as a result, the output, in theory, should have no mains hum. And again, if there's a harmonic here, delaying the harmonic by 2 or 3 or 4 cycles and subtracting it gets the same effect. So there's your comb filter, just removing the mains hum, and that actually works surprisingly well. I've got a low pass filter here to cut off the high frequency stuff and stop aliasing, and then it just goes into an audio sink and a waterfall. And this is what that looks like. I'll stick this GRC file for this probably on the Discord somewhere, just so that people can use it if they're interested. But this is a signal I recorded a couple of days ago during the day. There's not much going on here because it's not at night. This signal here, these are lightning strikes, these solid bars, and you can see they more or less go straight across the frequency range. And of course, if you imagine the top part moving more quickly than the bottom part, that's where you get the kind of curved shape that would be produced by a whistler. This thing here is noise of some sort. I'm not sure what piece of equipment that my neighbors have produces it, but that's noise. And you can also see there's a switching on and off as somebody's turning on an electrical appliance somewhere in my neighborhood. But again, noise is a problem at these frequencies, but you can still hear the whistlers or the clicks through this noise. And generally things tend to be quieter late at night anyway, because most people will switch their equipment off, or they won't be using it earlier in the morning. So the amateur bands. This is where you can not only receive, but if you construct yourself the equipment, you can transmit as well. The 2200 meter band, 135.7 to 137.8, normally Whisper or FT4. We're allowed to transmit 1 watt EIRP in Ireland. EIRP, as you probably remember from your exam days, that's the equivalent to an isotropic antenna. But because the isotropic antenna for these frequencies would be, well, 2 kilometers across, you're not going to get that, and you're going to get a much reduced antenna gain. The antenna gain for a dipole is roughly the square of the frequency difference. So I've just shown here a quick calculation, 2200 divided by 160. If I'm using a top band antenna, which I would be, to get 1 watt radiated out of it, I need to pump in 189 watts of RF. So my conducted power needs to be a lot higher than my radiated power. In fact, because my loop is probably a bit better than isotropic, it's got some antenna gain, 2 or 3 dB. So I'd probably reduce this to about 100 watts or so. Because you're only transmitting 1 watt EIRP, and because your antenna isn't very efficient for receiving either, you will need a preamp to be able to receive the signal. But once you've received the signal, it should be possible to decode it with normal sort of Whisper or FT4 software on your computer. And people do make contacts on this band. There's only a few stations making contacts on these bands, but they do exist, and receiving them is fairly easy. Transmitting back is probably a bit more of an adventure, but certainly it's on my to-do list. The 630 meter band, again, this is now kind of medium wave frequencies. Again, Whisper or FT4. 5 watts we're allowed in Ireland now. Because the antenna is only 4 times bigger than my Skyloop, that would mean I would be looking at 77 watts if my Skyloop was isotropic, probably about 50 watts or so. And building a 50 watt transmitter at this low frequency is probably not that big an undertaking. Again, you probably need some kind of preamp likely required for the reception, because this same factor here applies to receiving the signal. The received signal level is going to be very low, and it'll need some amplification probably before it even leaves the antenna site. So some kind of LNB on the antenna. And then, of course, top band, which I'm hoping you're all familiar with. A lot of transceivers do top band. It's probably not that challenging to build a top band receiver compared to a lot of other higher frequencies. It's almost crystal set level, and because we're allowed to transmit a reasonable amount of power on top band, it's reachable. This is probably the easiest amateur band in this frequency range. There are navigation beacons. I showed you in the kind of spectrum map. There are navigation beacons between or either side of our band. These transmit AM. They transmit Morse identifiers on the AM, but that's modulated tones on AM. It's not true CW. Sometimes they have airfield information too, not so much these days because nowadays everyone has the internet. The antenna on the aircraft is directional, so you can tell which direction the beacon is. You tune into it, you identify it, and you can then say, well, it's this heading. You cannot tell whether it's a heading or the reciprocal of the heading. So if you're flying along and you can receive this beacon and it seems to be to the north of you, it might actually be to the south of you. In the same way, southeast, northwest, whatever the reciprocal directions, you can't tell because you cannot build a directional antenna for these sorts of wavelengths that has any kind of front to back ratio. You'd be talking about a Yagi that would be bigger than the airfield, certainly bigger than the aeroplane. These can be easily received with an AM receiver, even a broadcast receiver. If you can tune it out of its normal range, you'll be able to pick these up easily enough. And I was able to pick up, here is one that's near me, it's Echo Oscar Kilo, which is one of the navigation beacons used for the Knock Airport approach. And you can hear that pilots don't really transmit Morse or listen to Morse terribly quickly. You think 5 words per minute would be vastly more than what a pilot needs. There are radio clocks. These are, again, fairly easy to receive. MSF in Anthorn transmits 60 kilohertz, and they transmit many tens of kilowatts at that frequency. And certainly where I'm living, maybe 1,000 kilometers from them, I can receive this without any trouble at all. And it can be received all over these islands. The DCF-77 transmitter on 77.5 is transmitted from Germany. And again, it's fairly easy to receive here. These frequencies are derived from an atomic clock. So not only does the atomic clock derive the time signal, but it also derives the carrier frequency. So these frequencies can be used for regulate or for monitoring your equipment to see how accurate it is. And those of you that were following the MF and down chat yesterday will have seen ChatGPT discover this for itself. So they can be very useful as a frequency reference, and because they have such accuracy. There's transmitters in France. There's a USA transmitter of 60 kilohertz. There's a transmitter in Japan. The France one is a bit different. It's not transmitted as basically CW, which the others around here are. The France one is phase shift. So the transmitter is a continuous carrier, but they change the phase to transmit the time signal. These can be received with a sound card that goes up to higher frequencies. So a 192 kilohertz sound card will pick these up with not too much difficulty. If you've got a receiver that will receive CW down at 60 kilohertz, that will pick up just fine. And to be honest, they sound like Morse. They sound kind of like this. And that's the MSF signal. And there's a break every second, but the length of the break is what encodes the time. So short and long breaks are what provides the data that enables your radio clock to tell you what time of day it is and things like that. Okay, submarine stations are all the way through from 18.1 to 145. Again, these are tremendously powerful transmitters, and you can receive them from a great distance away. Again, you can receive these with a sound card, and you can hear them, and you can hear the modulation. You're probably not going to be able to decode them, but you can hear that there is data there, and you can. I've had some of that decoded, and you just, of course, get pseudo-random data because of the heavy encryption. The Russian station, RDL in Krasnodar, is quite interesting because they change modulation type. They have a kind of multi-symbol FSK, which they transmit most of the time, but they switch to a two-tone signal, which sounds like it might almost be like FM Morse. And I'll just play you a bit of that, and you'll hear that there's two modulations. There's the multi-tone, and then it switches to the two-tone and back. No, I think it's not enjoying the noise reduction in Zoom. I don't know if you can hear that some of the time it's alternating between two tones, and some of the time there are multiple tones going on at once. So that's alternating between two tones. If I switch to this recording, this is all multi-tone. Oh, sorry, no, that's the wrong one. If I switch to this recording, they're all multi-tone.
It's just about coming through, Simon. I think we can hear it.
Yes, okay. Again, I can stick these recordings on Discord if any of you are interested. If you're interested in receiving the SAQ transmissions, I find being able to receive these, they're a good indicator that your sound card is working okay, and particularly these lower ones for things like the 18.1 will receive from any sound card, and you should be able to pick them up without too much trouble. It's probably best not to send them a QSL card though. This is one of my favorites. In Grammaton in Sweden, they have the last surviving Alexanderson transmitter. It was constructed in 1924 as a way to relay telegrams across the Atlantic, and it produces 200 kilowatts at 17.2 kilohertz using an alternator. So there's no transistors, no valves, and no electronics at all, just a slotted steel rotor, which is 1.6 meters. So what's that? 6 feet, 7 feet ish, by 75 millimeters thick. And they spin this thing at 2000 RPM, and the slots go fast enough that it generates this 17.2 kilohertz tone. They transmit CW. Originally, they were using it to transmit the telegrams across the Atlantic. Nowadays, they send often a Christmas Eve message, and the closest Sunday to July 2nd on Alexanderson Day, they'll send a message as well. Again, you can easily receive this with a sound card. If you can pick up the submarine stations well, you'll probably be able to receive these, although it does depend on conditions on the day, unfortunately. But they are very happy to get a QSL card from you, and they will stick you in their charts of all the different places around the world that receive them. I've got a recording of them. One of the interesting things when you listen to this recording, they're transmitting CW, but when they key down, this huge disc is slowed down by the drag to produce the RF. So you can actually hear the tone drop during the dash part as this huge disc is slowed down by transmitting all these 200 kilowatts. So here is a quick snippet of one of their transmissions. And you can hear there the way the tone drops as the disc is slowed down by their transmission there. So I'll just finish off with a picture of their transmitter. You can see, I think the guardrails give it a sense of scale. These are the sorts of guardrails that you'd get in any kind of museum. So you can see this thing is certainly taller than you or me, and it's an enormous chunk of 1920s engineering, but there's no electronics in that whatsoever. It's just a big generator. And that was what I wanted to share with you. Are there any questions?
Thank you very much, Simon. That was wonderful. And I did not know that it was so simple to build circuits for this stuff. That's ridiculous. Does anybody have a question that they would like to ask? If you want to unmute yourself or turn your camera on, that's fine. Or we'll take questions in the chat from anybody who doesn't want to do that, and I'll relay them. Nathan, you've got your camera on, so I'll call on you first, assuming you've got something.
You've put me on the spot here. No, it was very interesting, Simon. Thank you for doing the talk. It was much appreciated. As you say, it looks like there's guardrails there, so I'm assuming that's an open museum you can go and visit if you're ever in the country.
Yeah, and you can go. They let people in when they're running it on the 2 days a year. You'll see YouTube videos of them running it, and various people coming and visiting and watching it in action. I would certainly love to see it, and it's on my to-do list if I find myself in Sweden.
I think it'll certainly be a summer trip. Unfortunately, I work in retail, so Christmas Eve's out of the question.
Definitely.
That's a shame. I was just interested. I looked up during the talk what the lowest frequency transmission station on Earth is, and apparently it's just shy of 12 kilohertz is one of apparently Russia Alpha stations. I don't know if those are still going on.
They are still going on.
Oh, they are. Okay. I assumed they'd been
Yes.
phased out, but I thought it was interesting when I saw your 10 kilohertz figure. I thought, well, I'll check how far above that the lowest frequency used is.
Back in the days, the submarines used to have a transmission station which was transmitting in the tens of hertz region. So the Americans had a tens of hertz transmission, and the Russians did as well during the Cold War. So and their antenna, which is again a fraction of a wavelength, stretches halfway across the US. It's and mad stuff.
I think I have read about that, but I didn't realize it was quite that low. Oh, somebody is joining us a little late. Hello, welcome. We're just at the end, but we did record everything. Hello, future YouTubers. Does anybody else have a question at all that they'd like to shoot Simon?
Hi, can I just ask one question, please? Simon, thank you so much for your talk. It's been really interesting. Is there a resource anywhere where you can find a frequency list detailing where these submarine stations?
As actually a lot of them are on Wikipedia.
They are. I posted a link in the chat. If you scroll up, Philip, I did pop a little link in there to thank you, other Simon. Much appreciated. Yes, so there are things there.
That's lovely. Thank you so much. I didn't see that, but no problem. But no, thank you so much for that.
Yeah, no problem. Philip says the Swedish transmissions are not slow Morse. Okay.
No. They are full speed Morse, and they're a bit beyond my ability to follow, but they work fine on things like FLDigi and the like. Right.
Derek, you have a question about the whistlers and the lightning stuff. Go ahead.
Yeah. Okay. Can you hear me?
Yeah, loud and clear, mate.
I can hear you.
Okay. Yeah. First of all, it was a great presentation, and I wanted to ask about the lightning whistlers, specifically about the kind of antenna that would be suitable for this, because we have seen with the ferrite antenna that you have shown that it has a relatively low fractional bandwidth, right?
Yes, but that's because the antenna there has a tank circuit in the front end. It's not. It's possible to build a ferrite rod antenna that has a better frequency response if you don't use a capacitor, but you just take the inductor through a resistor and into the JFET. You should be able to receive quite a broad frequency range.
Okay, thank you. I just wasn't sure if you can contain the entire bandwidth of the sweeps of those signals with a ferrite antenna, but you can.
Yeah, you can.
Okay, thank you.
There's lots
Excellent.
of circuits online for how to construct circuits to pick up whistlers and things like that.
Fantastic. Vic, you had a question. Hello there. Oh,
Can you hear me, guys?
hello,
Vic.
gotcha. Fire away.
Yeah. I'm on the phone here, just doing things around the house. Thanks, Simon, for the talk. I was in that seat last month. Enjoyed it entirely. Hope you did as well.
That's a lot of fun.
Quick question: do you have any tips and tricks for people to reduce the noise and interference?
Now the obvious things to do are the things that we would all do to reduce interference in the shack anyway. Try and find noise sources by turning off the power and things like that. Unfortunately, you need some quite hefty ferrites to do things like reducing, because at these low frequencies, the impedance for your ferrite isn't terribly high. You saw with that 60 kilohertz ferrite rod, that is on the outside of the house and has a feeder coming in. I think really just you're trying to get away from other sources of noise. If you've got an antenna that's outside, away from other sources of noise, and you've got an amplifier on that in order to boost the signal up, then you can get past a lot of the more local noise sources.
So ferrites and mass and
Yes.
ferrites everywhere.
The other advantage of the ferrite rod antenna is it's directional.
Yes.
And as a result, you can often turn them to avoid a noise source.
Yeah, I was going to say that's one of the good things about them. Having never tried one myself, I'm looking forward to giving it a go. I suppose cleaning up the shack power as well. We always recommend the GM3 SEK presentation, cleaning up your shack, linked ad nauseum on OARC, but always welcome. Anything you can do, I imagine, is gonna make a difference.
Yes.
We have. Oh, there's a nice picture there from Simon with a nice little loop there in a loft, I guess, or in the roof space. So that's quite nice. I might take that and pop the picture on now so everybody can see it on the video. We have 1 or 2 minutes left. If anybody has any other further questions they would like to ask. One thing I did think about, Simon, is that maybe we could knock up an OARC wiki page with perhaps some information on how to get into this and to links to resources and things like that. Maybe that's something we could do.
Yeah.
And also the sound clips as well would be quite nice on there.
Yes,
So
the
we can
SAQ
do that.
the SAQ transmissions, there's already a wiki page for.
Aha, excellent.
And that's probably a good place to start looking at these frequencies, because a lot of the things that apply to SAQ also apply to other things. The waterfall display I've shown you and the tuner that goes with it is a simple GNU Radio companion flow graph that I put together and stuck on the wiki. I can put the spherics flow graph on the wiki as well.
Cool. That would be really helpful. No problem at all. We are at 8 o'clock and the Rubber Duck Pub is just about to start. And I know some of us will be heading over there. So thank you once again, Simon. EI3JDB is Simon's call sign, and there's things on the internet if you want to go and look up that stuff. Thank you all for attending, and we will be back again next month, as I said, for Introduction to Satellite Operation from M5 JFS. That will be on the 5th of September. Until then, see you next time.